Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
I'm going to give you, first, a little bit of context, the kinds of things that we've been doing. I'm just going to play a quick video, and this video is kind of old now. It's about 3 years old, but it gives you the basic idea of the stuff that we've been working on. On the left-hand side, you see a phone app here that pops up on your tablet computer or your phone. And when a person walks into the room, he turns on the light switch, you see a little light switch pop up here. You see a black icon follow him into that first room, and then when he turns pushes the button on the remote control, the television pops up in the screen. A second person walks in, and you see that purple icon follows him into that first room too. He walks through the first room into the back room, and the purple icon follows him again. And so the key here is that the system somehow knows the first person is still sitting in that first room, whereas the second person has gone on into the back room. And it can differentiate these two people. Now, the people aren't wearing any RFID tags, aren't wearing any RF transmitters. It can figure out who's who without them actually carrying anything or participating in anything. And it also monitors you saw a water fixture turn on, light fixture turn on, now you see a microwave turn on. And as this person walks out of the room and out of the field of view, in fact, of the camera, you can still see in that screen over there, he walked out into the hallway, through into the bathroom, turned the light on, flushed the toilet, and yes, he washed his hands. Now he's going to leave the bathroom, turn off all those fixtures. So the basic idea here is to monitor who's in the house, which room they're in, and then what they're doing in terms of electrical appliances and water fixtures. Let me cut this video short just a little bit. The basic idea, and I'll explain how that video is actually made. So the basic idea is you walk into a house and you deploy a bunch of these, what we call doorway sensors, door jamb sensors, at the top of the doorways. And basically, that's all you need to do. There's no configuration required. You walk out of the house. When you come back in, you can open your phone, and there's the app that you just saw. So it automatically figures out the floor plan, figures out the people, the identities, and where the fixtures are and what fixtures are going to be used. So what's actually in this door jamb sensor? There are a number of things here. One is a motion sensor. It's pretty simple. There's one on each side of the door to monitor motion in both doors, in both directions. There's also a door latch sensor, so it can tell, for those doorways that have doors at least, whether the door is open or closed. Inside this enclosure, in our current version, which you'll see a little bit later today, there's a temperature sensor, two light sensors, one in each direction, and a magnetometer. And the last and most important sensor here is an ultrasound sensor that points down. It's actually an ultrasonic rangefinder, points down into the bottom of the doorway. And the reason for that is to figure out who's actually walking through the door. So you can imagine a conical sensing region of this ultrasonic rangefinder. When the person walks under the door, the distance measured at first points to the floor, so about 7 feet, plus or minus. When the person walks through, you get a shorter distance, the distance from the door jamb to the top of the person's head. And that can tell you roughly the height of the person, the difference between those two readings. And you can identify which is the position where the person walked directly under the door, hopefully because that's the shortest distance that you measured. Now that tells you who walked in the door, more or less, differentiating between the people in the household, at a household scale, where you have 4 to 5 people living there. It doesn't tell you which direction the person went in, so you don't know which room they went into. But if you just take that ultrasonic rangefinder and tilt it a little bit, now you have an asymmetric sensing region, and that generates an asymmetric response. So if the person's walking this direction in the doorway, along with a cone, the shortest distance you get is right away, whereas if they walk the opposite direction, you get the shortest distance at the very end of your measurement. So that tells you who the person is, roughly, and which direction they went, so which room they went into. And based on that, well, I won't go into the details of how we generate this floor plan, but we can generate the floor plan based on that information, and then identify where the people are moving throughout the house. And then we take that information, which is just tracking information, and fuse that with data that hopefully is already being collected at the house. Water mains data and power mains data. So over time, the person just walked into this room here. Over time, you're also collecting electrical mains data and water mains data. And you might see that when the person walks into this room, you often see some usage on the water mains. And that usage happens to look kind of like a toilet. So you might assume that there's a toilet in this room. And maybe you see some more water mains data being used, and that you might assume there's a sink, because that looks like a sink profile. So now you can identify what kinds of fixtures are in each one of these rooms. A person might leave that room, go into a different room. And in this case, maybe you see some electrical mains data that looks like a light bulb, and it also looks like a television. You can assume that room has a light bulb and a television in it. And from that information, we repeat that for all of the electrical and water fixtures over time, learn this profile. And then, based on the kinds of appliances and fixtures that you have in each room, also try to figure out which room is which. So any room that has, for example, a toilet in it is probably a bathroom. It's certainly not a bedroom. If a room has a stove or an oven in it, it's probably a kitchen. And so based on just these doorway sensors, along with the power mains and water mains data, we hope to identify the floor plan of the house, which people are in the house, which rooms they're in, and what they're doing in terms of electrical and water usage. And once we have that information, as somebody walks around the house and they turn on, for example, a light switch, turn the light on or change the heat or whatever they do, turn on the television, we can monitor what they're doing over time and assign, let's say, those usage events to that individual person. Usage of electrical, water, heat, whatever it might be. And one goal of that could be to turn that around and use it for feedback. So you might generate a graph that looks kind of like this, where instead of saying something like, this household uses so much energy compared to their neighbors, you can say, this person uses this much energy compared to their spouse or their children. And you can break that down by person and also break that down by fixture. And so we can say, it might happen to be that, dad takes really long showers and mom uses more lights in the house. And we can also hopefully identify what kinds of waste. So this is, we're not generating these graphs right now, but this is our goal. We can identify waste. For example, mom does use more lights in the kitchen, but it might also be true that she's not actually in the kitchen when she turns the lights on. So that's waste. We know that, and the same for a bathroom or bedroom. So hopefully identify the difference between usage and waste as well. So this is some of the stuff that we've been doing and are trying to do as we go on. To do that, we basically need three kinds of sensors, shown up here on the left side, top left. There's a doorway sensor, which goes into each door. And then there's power mains data and water mains data. And those sensors are being deployed already across the country and across the world. In total, this is about 15 sensors. So the average house has 10 to 13 doors plus 2 main sensors, so about 15 sensors. We also had, before we did this, we did a bunch of exploratory studies. So for example, we took several different kinds of motion sensors and placed them in different locations in every room, on the walls, on the doors, above the windows, to see where we would actually get the best motion sensor data. Same thing for temperature sensors. Put them on the exterior walls, interior walls, near the doors, near the windows. And light sensors also, same thing. So in our exploratory studies, we had to actually deploy about almost 200 sensors per house in some cases. And then we also, while we're doing our studies, have to collect data on the actual fixtures. We use what we call ground truth sensors, like this one here that actually has, this is actually a contact read switch that detects when that handle's moved, so you know when the fixture is being used. That way we can check whether our estimates of the fixture usage are correct or wrong. And so per house, we need to monitor every light switch, every appliance, every water fixture. And so that's about another 100 sensors per house. So you can see that in total, there are a pretty large number of sensors, on the order of 300 or more sensors per home. And of course, this can't be done just in one home, because if you do a study on one home, it doesn't mean much, right? It could be a fluke result. So you need to deploy this entire system into multiple homes. And in the end, after doing these studies, we ended up deploying over 1,200 sensors in 20 homes for up to a year, sometimes more than a year at a time. So this is one of the main challenges, scaling up these deployments to do the kinds of studies that we've been doing. Now, I come from the field of what we call wireless sensor networks. One of the main goals of that research area is to get large-scale deployments working reliably in extremely harsh environments. In fact, people in that community would probably say it's not even a hard deployment if it doesn't take snowshoes and a pickaxe to deploy it. So when we came into this research, we thought deploying sensors in a house would be pretty much as difficult as taking a nap on the couch. And in many ways, that's actually true. There's a huge variety of off-the-shelf sensors you can buy. They work turnkey, more or less. But it also turned out that there were a large number of challenges, especially when we got to scale. So we found that the difficulty of these deployments, shown here on the y-axis, increases dramatically as we move along this x-axis of scale. So for example, and there are specific thresholds where it became very difficult, shown here in yellow. So for example, as we increase the number of sensors per house, deploying a small number of sensors is pretty easy. But as the number of sensors grew larger than the number of power outlets in the house, things got really difficult. Deploying in a small number of homes was pretty easy, right? Just to plug them into the walls. But as the number of homes outgrew the number of researchers in our group, then it became very difficult. And also deploying for a small number of days was fairly easy. But as the number of days grew to more than about a month of time, then things became more difficult as well. And this graph here, this little yellow region, the phenomenon that I call a phase transition, where things go from being fairly easy to all of a sudden being very hard. That phase transition is kind of one of the things that makes me a big believer in the lab of things that I guess you'll hear about later today. And so this is what I want to talk about, and I'm going to go into each one of these three in a little bit more detail. Question?
So a month number is that's predicated on hardware or software reliability, or just mean time to some human kicking over a sensor?
It turns out that, yeah, the month, well, I'm estimating here. There's a lot of, there are a lot of reasons why. But
what's the bottleneck?
one thing that starts to kick in around a month is participant fatigue.
So kick over the sensors then.
That actually is true, yes. That's basically what happens. They'll start to unplug the sensors, for example. Yeah?
So you said participant fatigue. What do we actually have to do?
Well, it depends on the study. I have a whole slide on that. In terms of participant fatigue, what do they have to do? That's a good question, because you can see from the early description I gave of our sort of general vision, the goal is not to have the user participate at all. But users are very useful in terms of generating information, and so we'd like to engage them in these studies if we can. And the question is, what can we get them to do? So I'm going to go into that in a few minutes. So let me go into each of these three in detail. Number of sensors, what happens as you scale that up, number of homes as you scale that up, and the number of days as you scale that up. So the number of sensors was the first thing that we found, because we did it in one house. And one of the main challenges we found was powering sensors. So a main difference between deploying out in a mountaintop or a volcano or a desert and deploying in a house is that houses have AC power. So that makes a lot of things much easier. But it doesn't make all of your power problems disappear. And one of the things that we found to be a challenge is that there are only about 30 or 40 power outlets in a house. And we always thought there was plenty of power pretty much everywhere. But we didn't think about then counting the number of outlets. In one deployment, we did over 300 sensors. We only had 30 or 40 power outlets. So that means most, by far, the vast majority of our sensors did not have power. They couldn't use power. So we're still in the paradigm of battery-powered, low-power sensing. We also found that even if we did want to use these receptacles, we often had to run long wires. So you don't have power, for example, on the middle of the wall or top of the door or the top of a window or in the places where you want to deploy your sensors. In one house, we had over 250 feet of wire just to power 13 sensors. Running these wires is very costly, of course. We also found that the sensors that we plugged into the walls ended up having actually 2.3 times more downtime than the battery sensors. And there are a number of reasons for this. One is what you said earlier, people kicking the sensors over, and in fact, unplugging them. People would unplug the sensor in order to plug their hairdryer or their vacuum cleaner or something else into the wall. There would also be wire disconnections. If you're running long wires, it's likely to get snagged. It's very hard to conceal wires perfectly. And mobile objects. People moving around, or Roombas, or things like that. Children, animals. So even after, in one deployment, even with expansion adapters, we ended up in one house occupying all of the free receptacles besides 6. We left 6 for the users, not really thinking that the users would actually need power. And that turned out to be a big mistake. A lot of those sensors became unplugged. So the fact that we have 30 to 40 power outlets in a house doesn't really mean we have free power everywhere. And of course, the wires also would get unplugged. And it turns out that we had more maintenance calls per plugged sensor than we had maintenance calls per battery-powered sensor. And the reason for that is that if you've got a sensing subsystem and you have one sensor in that system run out of batteries, you can be pretty sure that the rest are about to run out of batteries. And so you change all the batteries for all these sensors. But the plugged-in sensors fail independently. They're unplugged in different places for different reasons. And every time one is unplugged, you need to go back and do a service for only that one sensor. There's no way to prevent the other sensors from becoming unplugged later on. So homes weren't the power panacea that we thought they'd be. We also found that they are not the connectivity panacea that we thought they'd be. Of course, getting connectivity across mountains or across fields is very difficult. We thought a small house, Wi-Fi works in houses, laptops work in houses. We thought connectivity in houses would be pretty easy. It turns out that it is for laptops on your couch, but it's not so easy when you start taking sensors and deploying them all over the house, like, for example, in metal air ducts, or in metal junction boxes, or on masonry walls. We had one house that had copper siding, so it was basically a Faraday cage, concrete floors, so it separated every floor into a different wireless network. So wireless connectivity in houses was pretty easy for people, but not so easy for sensors that are placed in obscure places that weren't great for wireless transmission. One alternative to wireless is power line communication. So we thought, well, if we can't use wireless, we'll at least use power line communication. That'll solve our connectivity problems. But power line communication only works for those sensors that can be plugged in. And I already explained why it's hard to plug in most of your sensors. And so if you can't plug it in, you can't use power line. The off-the-shelf power line modems that you can buy at Staples work pretty well, but often they're more expensive than the sensors we're trying to have communicate by several times. And it turns out that studies have shown the sort of low-cost power line modems that people use for low-power sensing don't necessarily give you a very high data rate, and they also give you pretty high latency because of the noise on that signal. So it's very hard to get power line communication to work, too. So homes turned out not to be the power panacea or the energy power panacea that we were talking about, and they start to look a lot more like these remote sensing environments. One of the benefits of working in a house is that there's a whole industry, the home automation industry that's been working on these problems for a long time, and they sell lots of off-the-shelf parts. But it's not just the number of sensors we have or the number of places we need to deploy them, but also the number of types of sensors that we have to deploy. And we have to start buying products from lots of different companies. And if this is just your basic home monitoring infrastructure where you've got a router connected to the internet and a relay machine, every time you want to deploy sensors to do a different task, you need to buy a different kind of sensor. And each one of these sensor types comes with a whole new set of data and connectivity paths and hardware gateways and relays and software stacks. And so deploying 10 different networks in one house is very similar to deploying 10 different sensor networks in 10 environments, because they each have their own set of independent risks and failures. And so multiplying the number of types of sensors multiplies your probability of failure pretty quickly. And the calculus of mean time to failure applies to sensors in the house just as it does sensors outside in a remote environment. Right? A small probability of failure on one sensor translates to a large probability, a high frequency of failure for the whole system. So those are some of the challenges we found when scaling the number of sensors up. We also found it's hard to scale the number of homes up. In particular, like I said, as the number of homes becomes larger than the number of researchers, because it's easy to deploy in your own home. But once you start deploying in somebody else's home, it's a very different story. The participants in a study make a big commitment to your study. And they might be willing to say, we're willing to have your sensors in our house all the time, but they're probably not willing to have you in their house all the time. And if you want to go to the house to fix something or collect some data, you need to make an appointment, even for just a 10-minute stop. And if you stop for 4 hours, that's now disrupting, for 4 hours or more, you're now disrupting their meals and their daily schedule. And the number of times you're going to get a whole day to do a deployment is really, really limited. So we went through large efforts to try to minimize our time in the homes. For example, we'd go to the house once, scout it out, identify exactly which sensors we needed, where they would go, mark that down on a map, what types they are. If there are wires, how long are they going to be, so we can cut them and prefab that in the lab. If there are doors, we need to measure the widths. If there are pipes, we need to figure out how big the opening is to get to that pipe, how far how small of a person we need to get through that crawl space. Basically, think of everything in advance. Manufacture everything in the lab if we could. So pre-manufacture. pre-label, mark all that down on some floor plans that we had drawn out. And finally, when we're ready, go back and deploy. And of course, we needed to bring a checklist to make sure we had everything there, including spare parts, spare batteries, flashlights, garbage bags, vacuum cleaner, anything we needed. And if we forgot one thing, that cost you an hour because you had to drive out, go get it, and come back. And you only have, let's say, 4 hours. So doing these deployments themselves was very difficult, and maintaining them was very difficult. And so scaling up to a large number of houses was hard. And you can imagine where I'm going with this. This is one of the reasons why people don't want to deploy hundreds or thousands or hundreds of thousands of homes that are required in some studies, as a single researcher. And then finally, we found that scaling up the number of days was hard. And so this is one of the things, a couple of questions have already come out on this, and I'll explain why. One of the things was user participation that exhausted itself pretty quickly. So in a typical wireless sensor deployment, we have a battery, and we want to figure out exactly what to do with that battery. We can either use it very intensely for a short period of time or very slowly for a long period of time. And it turns out that we found our participants to be very similar. They would do, for example, push a button when they walk into a room. They'd do that for a couple of hours. They might wear a wearable device to track them around, maybe for a couple of days. They might self-report, so report on what they've been doing or where they're located, but they might do that for a couple of weeks. They might take surveys. They might do that for a couple of months. But we can't get them, for example, to push a button every time they walk into a room for a couple of months. Question?
Taking your battery analogy, so if you pay them, does the battery charge or it's never the same again?
That would be a very interesting study. But the question is, if you pay them, can you recharge this battery? So we found our users are very much like a sensor in the sense that they've got a battery, and they've got a finite energy supply. And we can either use that very quickly or use it slowly over a long period of time. If you pay them, do you increase this? I'm not really sure. That would be a really interesting study to do. Sorry, what was that?
I was just thinking you have to reduce the maintenance for the users.
Yeah, so the farther down that scale we get, the longer we can get the users to participate. Often the information we needed burned out we burned our batteries after about a month. Maintenance is also a problem, right? If the sensors are breaking all the time and people have to come in, you're exhausting their time commitment, your time commitment with them. So
how does that distribute across, say, age groups and families with kids versus single families?
Okay, good question. So how does that distribute with age groups and families with kids or not? I think if you have a single experimenter, a single researcher living in their own home, then they might have a bigger battery, bigger lifetime. But what we found is that this general trend is true even for researchers. And as I found out myself, even if you're a researcher, then you have participants in your home, like spouse or children, who don't necessarily have the same incentives that you do. So in a lot of homes, you will have a limited, let's call it a limited battery, no matter what. So I think this applies even for participants, and especially you mentioned children and other kinds of commitments like this. One of the reasons why we found this to be true is because people have in a house. I think participating in a study like this is much different from participating in your office. Right? In a house, you have life to live, and you can't just stop everything you're doing in order to participate in a study. Whereas in an office, you can kind of trade off some of your tasks. Right, it's work anyway. So in addition to user participation, we also found that over time, as time increases, aesthetics become much more important. So in our early studies, we had wires and circuit boards and sort of all over the place. And you can see here exposed circuit boards. Over here, we've got a light switch with a little sensor on it, and every time you try to flip the light switch, you snag that wire. So this kind of became very much of a challenge, and our next generations of work, based on feedback from our participants, was to make all these sensors disappear into the woodwork. So what we found is that the aesthetics of the system is not just a superficial concern. It's actually a fundamental constraint on the lifetime of the system. Ugly or unusable systems are not viable over the long term. So it's a threat to the lifetime of the system. Our later systems did what we call disappear into the woodwork. So we've got a sensor here that looks like a regular light switch. We've got these other sensors that sort of what we call disappear into the woodwork of. They look kind of like a door jamb on the sensor on the door. besides the sensors disappearing so people didn't see them and the wires hopefully hiding, we also found that it's important to make sure that our sensors disappear even after we remove them. So, for example, tape on the walls will peel your tape. If you put other solutions like putty on the walls or staples, staples leave lines of holes. Putty doesn't necessarily stay very long. We've had one house with several hundred sensors where the sensors, because of the temperature rise and fall, the putty would harden, and then we'd get sensors falling off every 4 to 6 hours. Somewhere in the house there would be a sensor crashing to the floor. So after the sensors come off, they also need to be aesthetically sufficient. And another problem is LEDs at night. So we all know that LEDs at night, on your television or on your alarm clock, that's a problem. It's annoying. Sometimes in a room you might have a television or a VCR. But when you start to have hundreds of LEDs across your house, it becomes a showstopper. It's no longer just an aesthetic concern. So we estimate that one of our deployments caused 150 LEDs to be deployed in one house. And during deployment, during the day, it's actually not obvious. We can't see them at all. But at night, the users complained of it being a laser light show or a circus in the house. And turning the lights off didn't make a difference because it didn't get any darker. So this turned out to be a big challenge. And these are the things that, over time of deploying, these are the things that cause major issues in our deployments. We also found that noise is a big problem. So, for example, in one house, for reliability reasons, we deployed a UPS. We didn't have a laptop, so we deployed a desktop with a UPS. And at 5:30 in the morning, the power goes out, and of course, this thing is beeping incessantly. All of the plugs got pulled out while they were trying to figure out how to stop the beeping and go back to sleep. Then we, of course, had to make an appointment to go back and put it all back together. That took several days, getting all the systems back up and running. Turns out that our system, we actually lost more data because of the UPS than we would have if we had not installed the UPS at all. So, like I was trying to say earlier, the aesthetics matter, and not just because they matter to people, but because they matter for the lifetime and the data integrity of your system. Yeah? Okay. And last, over the number of days, we found that hazards in houses start to become important as well. So in a remote sensing environment like a mountaintop, you might have extreme weather or wild animals that interfere with your deployment. But in a house, we also found that there are a number of unexpected things that cause your sensors to fail. And like I said, the calculus of mean time to failure applies here. If you have a small number of things that cause failures, your system's going to fail pretty frequently. So for example, children turn out to be a big problem. This looks like a pretty reliable, well-built sensor when you plug it into the wall, but to a child, this looks kind of like a toy, right? It looks like a space shuttle or something. Long term, you would probably, before manufacturing this, have built a screw hole to screw it into the wall, or screw it into that receptacle. We also found things like mobile objects. Brooms would pull the wires out, or mobile vacuum cleaners that would go around and periodically on a weekly basis unplug all of our sensors. We also have sensors that were deployed in somewhat precarious ways because it's hard to really affix sensors to things in a house. They're not built with sensing in mind. And you can't really rely on teaching the people who live in the house how to use this, right? So if you deployed this or if you lived in this house, you could probably do things without breaking it. It turns out that most of the time it was the guests or the cleaning service or something else that would cause these sensors to fail. And those are people that we didn't have access to for training. So a small number of hazards like this would cause failures on a daily, sometimes weekly, sometimes daily, sometimes multiple times a day basis. So just to summarize the things that I talked about, we found that AC power does not mean abundant and reliable power in homes. Wireless connectivity in houses isn't as good as we had expected it to be. COTS devices, commercial off-the-shelf devices, are a double-edged sword. They save you design time, but they don't necessarily save you deployment or maintenance time. Houses are kind of like remote environments, especially when you don't own them or know people or live in them yourself. User participation is limited. We can't rely on the users to be the sensors in the long term. The aesthetics are important. They're actually vital to the survival of the deployment. And we had a bunch of environmental hazards in a house. So things that we thought we wouldn't see outside of remote forests and mountaintops. So these are some of the things that we found to be challenges in homes. And This is basically what's made me, like I said earlier, a believer in the Lab of Things, something that would allow me to deploy a small number of deployments and also maybe share deployments with somebody else who's doing similar things in order to multiply our benefits from our efforts. So I just want to thank many of the students and other researchers who participated in this work, and I'll take questions.
Can you take the microphone, please? Yeah.
So it looks like part of the reason you had such challenges is because of the sheer number of sensors in the home. Have you looked at trying to create or define a minimal set of sensors for a particular application that might somewhat simplify things?
Yes, we have looked at a minimal set. And part of the sensing that we've done is actually what I call exploratory sensing. So taking lots of sensors and deploying them in different places at the same time, and then analyzing them post facto to find out which subsets are essential. And that's actually how we ended up coming up with a doorway sensor that has all these things integrated. But it took several hundred sensors in many homes to come to that point in the first place. And I think that study, of course, isn't conclusive. As people start to try to find other things out of the house, they're going to need to do the same kinds of exploratory studies.
So I have a question about, so you're trying to minimize the number of sensors, but as you've pointed out, when you start putting these technologies into people's homes, there's a lot of issues around how they affect the living experience. And what we found out in the 2 homes that we worked with is that now we have to consider adding additional sensors to be able to mitigate the impact of the technology. So light sensors that mean that we adapt the displays to the appropriate level of lumens in the room, and that they go off when there are things that when they go off when they should be off, or things that change according to proximity. And I'm wondering if you've thought about how these integrate into the larger picture so that you kind of get this optimal set of what's the data that we need to be able to find out what people are doing in the house, and then what's the sensing information that we need to be able to do to minimize the intrusion of the data collecting apparatus that we've got in the first place.
So who polices the police? That's an interesting question. And we haven't really thought about that. That's an interesting question.
That would be the last question, please.
I understand that you started with the kind of technical issues. So, and actually all of the problems that you listed are technical problems. But what's the benefit for the user? I mean, what are you waiting from this platform from the user point of view?
That would be a whole nother talk. So I could go in, so the first couple of slides that I gave, just to give some context of why we're doing this, I could give you another hour on that, but I won't.
It's not very clear the kind of new experience I can leave as a user in such a house.
Why would a user want an instrumented home? Is that the question? Well, you can get feedback about what you're doing. You could give people feedback about their energy usage, their medical, their health status, or potentially help mitigate shared resources in a home, like a car, or coordinate dinners. I think there are a lot of reasons why people would want sensor data in the house.
And last question, since I'm a European, I would like to know if the NSA will know what I'm doing in my home.
If who would know? Oh,
the NSA.
NSA?
Is it the NSA?
Okay, it's a good question. Privacy is a big concern for this kind of system, and I think it would be for anybody who's doing sensing in homes. And our data is not going to the NSA yet. They haven't subpoenaed us yet. So if this were deployed in a commercial product, is that a question? I think the goal would be to not send the data out of the house and to leave it all in the house. So there's something like a central control unit that collects the data, processes it, actuates if it needs to, discards the rest of the data that's not necessary. I think it could be secured. There are still, of course, privacy attacks, and we've done some work on inferring what people are doing just from encrypted data that's flying around the house. So it's a big problem, and I think that's a big aspect of the kinds of stuff that we're trying to do. This is up for debate, but some would argue that that's not going to stop the technology.
As a father, should I know what my daughter is doing?
I'm not qualified to answer that question, but I do think it's an important concern, and hopefully all of us are looking at that.
Thank you very much, Kamin. Thanks a lot.
Thanks.